Hello, we are Team Zebra, and our Capstone project is on printer real-time torque measurement. Our technical director is Matthew Corbasi. He's a UR grad of 2008, which is bachelor's, and of 2016, which is master's in mechanical engineering. Our team is composed of myself, Abe Gilbert, who's a computer engineer, Jacob Ribeiro, who is an electrical engineer, and Oscar Schnippering, who is an electrical engineer as well. So first, a little bit about the company that we worked with, Zebra Technologies. It is a multinational corporation that is headquartered in Lincolnshire, Illinois, and was established in 1969. It is a market leader in mobile printing technology, and as of May 2022, Zebra Technologies has a market cap of 17.8 billion. We worked with the Lincoln, Rhode Island branch for our Capstone project, which specializes in hardware and software development for mobile printing. The motivation of this project is a fixture design that interfaces the transducer and interfaces all peripherals to one device. And eventually that fixture would be on a PCB. A graphical user interface or GUI is created to handle the operations of the device and to gather the torque data from the transducer and output the data as a graph for the user to view. The anticipated best outcome is to interface the transducer and gather the signal data from the device and connect to the GUI to send that data to. It should be user-friendly. The GUI should also have an easy-to-use interface and allow for fast troubleshooting. And the setup would be applicable to many different types of printers. We had achieved the ABO, and on the left shows the GUI with the 4 parameters that would be sent to the printer at the very beginning. And right next to it is a graph of the torque data that is obtained after printing the labels shown on the right. Our team accomplishments included consolidating the STM32 code. So the input-output controller, or IOC, was linked with the C++ files for easier code generating. A voltage divider was created to lower the voltage to the needed level, since the torque transducer outputs a max voltage of 10 volts, while the STM board can only have a maximum voltage of 5 volts. So we needed that so the board would not fry. A low-pass filter was created for obtaining clearer data from the torque transducer, and an external trigger was added so that the torque data would be obtained at each step pulse of the printer. We also integrated the GUI, so data can be sent and received between the GUI and STM code. There's quality of life additions to the GUI, including an open save option that would allow the user to open previous session files as well as save current session files, as well as a button to scale the graph. The particle break was also created that would be able to emulate different printers and would be added to a separate fixture in the future. The economic impact of this project includes providing a better product that would increase customer satisfaction, and there would also be reduced costs with troubleshooting, as it'd be easier for the user to troubleshoot any problems with stalling of during printing, and there would be less return products because of this. This is our block diagram. So we have the GUI in the center that will first send the 4 parameters to the STM board. And then when the printer starts printing, it will send out a step signal to the board. And the stepper motor then will be synced up with the printer. And while printing, the transducer will gather data, which will be sent to the voltage divider and then the low-pass filter. And then finally, the STM board where after it is done printing, it will send it back to the GUI to be able to be viewed. My contributions included working with the STM32 code. I fixed the code from the previous year and worked with the IOC. Both the code and the IOC that is on the right were synced, so it's easier to co-generate. Implemented DMA or direct memory access. So the ADC torque data that is obtained would be directly put into memory. And an external trigger was added so that each time the printer puts out a step pulse, it will trigger the ADC to gather the data from the torque transducer. I also contributed to the GUI. So I connected the GUI to the STM code so data can be sent and received from the GUI. Open save button. So the open button, as shown on the right in the GUI, will allow the user to open up previous sessions and view the graph of the data. And the save button will be able to save the current session to anywhere that the user chooses in their computer systems. And then on the bottom right picture, that is the graph that is scaled. That was from the previous slides, so it's easier for the users to see each torque data point. And now I'll hand it off to Jacob Ribeiro.
Thank you, Abe. Looking at the block diagram, we can see that the transducer needs to have a voltage divider, since the signal coming from the transducer is a 10-volt signal. The STM board would prefer a lower voltage signal for its analog to digital conversions, so I was tasked in creating a voltage divider. The voltage divider's main job is to divide the transducer's voltage across two resistors in series to the output. The resulting resistor converts the 10-volt signal from the transducer to a 3.3-volt signal that the STM board is happy with. I was also assigned to help with the STM code in order to help troubleshoot issues and find ways to communicate the hardware side of the transducer and the STM board to the software side to get the data that we need out. I created a proto board with both the voltage divider and a low-pass filter that Oscar designed to ensure stable connections for the hardware to get a readout, and another proto board with a particle brake power supply that Oscar designed. The particle brake will provide smooth and repeatable torque controls that Oscar will talk about. Understanding the data that is coming out of the transducer is important in order to know what type of values we need to expect. The transducer gives us a voltage range that is used to calculate the torque measurements that we are looking for. With the voltage value and the range that we get from the transducer, we will calculate the torque inside the Python code in order to have the processing done off the STM board. I've helped create automatic file backups that will help a backup be made if the user wanted to save the data that was created from the system. I've also helped create a help button that will allow the technician having troubleshooting steps if something is to go wrong. The plot data from the data that was created has the ability to show you over time the data that was being generated. I will now hand it off to my partner, Oscar.
Thank you, Jacob. So having our final look at the block diagram, you can see that once the signal has been dropped down to 3.3 volts from 10 volts, it once again goes through a low-pass filter to remove any noisy high-frequency spikes that cause errors during the data acquisition process. For unknown reasons, the transducer has been known to output high frequency spikes that do cause errors during the data and printing process. So the low pass filter was designed and implemented to help get rid of them. You can see here I began by simulating the design on multisim. I believe the most important part was actually the simulating the noise I was trying to get rid of, because essentially a low pass filter is quite simple, but it was quite difficult to find a realistic representation of the noise we were trying to filter out. Essentially, we wanted all of our signals that we wanted were at 200 hertz or below. So that would have been our cutoff frequency. And using guidance from Mike Smith, I was able to come up with this design on multisim. And with the help of Jacob, I was able to implement it on a breadboard and test it. You can see here hooked up to an oscilloscope. You can see the top image shows a very noisy signal with simulated noise using a signal generator. And on the bottom is the output. And you can see the undesired frequencies have been attenuated, and that the cutoff frequency, that no signals higher than 200 hertz are able to, that no signals over 200 hertz exist because they've been attenuated by the filter. And my main focus for the second semester was to create a power supply for a power supply for the particle brake. I'm sorry. And essentially a particle brake is a device that uses current to generate a torque resistance, and that's an exact torque resistance that can be controlled using the specific amount of current that the particle brake receives. Now, you can see here in this center picture in the bottom right corner of it is the particle brake. It's a very relatively small, maybe device that looks like a servo, but the purpose of it is to provide a exact amount of torque resistance for testing purposes. Now, the company that manufactures these particle brakes sells a power supply for about $700, but we were able to recreate it for about $30. And the specification for this one was a 24-volt supply that can be controlled between 0 and 49.5 milliamps and that should be in equal steps. And the design is up here, once again done in multi-sim with the 467 ohm resistor acting as the particle brake. That's the internal resistance of the brake. And the R2, the 1550 ohm resistor, is what we are using as a potentiometer, or in this case, as a resistor decade box. So like the control for it. Now, in the original design, it needs to be constant voltage. It needs to be 24 volts, yet the current needs to change, and it needs to change in two exact values. Now, in the first iteration it is hardware controlled, just using either a potentiometer or a resistor decade box. But in the future of this project for the next year's team, we will hope that they implement a digital potentiometer, which can interface with the STM board using pulse width modulation, and then pretty much design a whole system where the exact amount of torque resistance that the brake is putting out is controlled by the STM board. And you can see that in the simulation, the multimeter is showing 49.508 milliamps. And in the hardware implementation, it's 49.565. And that's well within tolerance. And that's pretty much exactly the value we were hoping for and expecting. Here's a summary of our whole testing apparatus. You can see all of the different components we've talked about in this presentation, specifically the low pass filter and voltage divider, which Jacob put onto a proto board in a very compact form factor, along with the STM board and the printer, obviously label, and the torque transducer, which gathers the data for the entire project. And on the right is the hybrid stepper motor, which has a shaft which goes through the transducer and then into the printer, replacing the internal motor on the printer. And that was a demo of our project working. And you could see a label being sent and the label being printed and the data being acquired and the torque of the motor being shown in the GUI, and with the option to scale up to your choosing to get a better look at the data. And finally, we would like to conclude the presentation by thanking Matthew Kervisi, our technical director, Dr. Harris Sunak, the program director, Patrick Haggerty, another technical director, and Mike Smith, our consulting technical director, for his contributions. Thank you. Yeah, that was pretty good. What do you guys think?
Yeah.
Pretty good. Few like errors, but not that bad.
Did you guys catch the typo?
Typo?
But are we happy with that?
Yeah, I mean, I think so.
Yeah.
Okay, great. Stop sharing.